All right, welcome to week 4 of quarter 4 honors physics. We'll be looking at projectile motion in this particular week. We'll be learning how to analyze both the horizontal and vertical motions of an object while it's in free fall. All right, once again, you'll be going through this note section on the week 4 learning targets, watching this video. You will be able to compare and contrast both a projectile's horizontal and vertical motion. Mathematically, you'll be able to take a velocity vector, break it into its components, and then also reassemble it, which means to put it back together. You'll be completing the work for practice Google form as well as a week 4 project. In doing so, you'll be able to algebraically solve for various quantities, right? Initial, final velocity, displacement, position, or time, but in both directions, the horizontal and vertical. And just like last unit, you'll be able to create and read velocity and position versus time graphs, but you'll be able to do it in both the horizontal and vertical motions. A projectile is simply an object in free fall. So, in essence, in Unit 3, we were already looking at a projectile. The only thing with last unit is its motion was completely vertical. It was either dropped vertically or fired vertically. In this unit, we will now be looking at a free fall situation that includes horizontal motion, right, which I refer to cases 3 and 4. We'll either be launching things horizontally or firing things at an angle. Right, as you see in the figure to the right, this is an example of case 4. And notice the object has two velocities. These arrows represent velocity vectors, and things fired at an angle has a very large upward vertical velocity and a small forward velocity. Notice the x component of velocity remains the same throughout the motion, yet the vertical velocity, what we refer to as Vy, is changing by negative 10 meters per second, because that's the acceleration due to gravity on Earth. Now, mathematically, this is what you need to be able to apply in this unit, right? All vectors, in this case, we're looking at velocity vectors, can be broken into its x and y, right? Or horizontal or vertical components, right? In this picture, the white arrow represents the total velocity vector, the red represents its vertical component, and the green represents its horizontal component. You'll still be dealing with plus or minus, right? So anything up or right would be referred to as positive. Things fired left or downward would be treated as negative. Now, what you actually do to break something into its components is you use right angle geometry, right? So your SOHCAHTOA, you can use both sine and cosine to kind of figure out any unknowns, right? So in this example, right, C would represent your total velocity vector. A would be your horizontal component of the velocity. B would represent the vertical component of the velocity. As you're working in the slide notes, click on this little video. It's about a minute or so, and it will give you a nice visual of what the sine and cosine means in terms of the components versus the total velocity vector. So do that on your own. It should help you understand why this breaks things into components for you. Now, sometimes you're going to have the total velocity vector, right? And you'll break it down into its components, right, using sine and cosine. But sometimes you'll have the components and you'll be able to put them back together, right? So in this little example here, we have a fired projectile with a vertical component and a horizontal component of speed, right? You can put those two components together using Pythagorean theorem, right? This would allow you to get the total velocity vector magnitude. But in order to completely describe it, we'd also need to report the angle of the fire, right? And if you have the two components, we can use the inverse trig function, specifically inverse tangent of the Vy divided by the Vx to get the angle of launch. Right, so you see in this example here, if we use Pythagorean theorem, we get the total velocity vector. And if we make sure our calculators are in degree mode while using the inverse tangent of 2, we get that this is a fire of 63.4 degrees, which makes sense because the vertical component is larger than the horizontal component. These two hyperlinks here are interactive practice of a perfectly horizontally launched projectile. And then the other one is of an angle launch projectile from the ground that goes back to the ground, right? Embedded videos here of myself working through the example. Please go through them. This is where you'll practice your algebraic problem solving of projectiles. Okay. Our last three slides here work through the graphing of projectile motion. Right, this looks very similar to last unit. Right, if you were graphing velocity versus time, we can do it for both directions. Right, so we still once again get a linear equation where the final velocity is equal to the initial velocity plus the product of the acceleration and time elapsed. The big difference between horizontal and verticals, the horizontal acceleration is 0. So what happens, right? There's no AT term here, which kind of tells you that the velocity in the horizontal direction is constant. That will lead to a horizontal line when you graph it. You can still interact with this Desmos graph. On the other hand, in the vertical direction, we do have acceleration, right? It's negative 10 meters per second squared. So then you'll get a negatively sloped line if you're plotting vertical velocity. Specifically, it will be negative 10 meters per second squared, the slope, okay? The y-intercept would still be the initial velocity that you have at the beginning of the motion. Right. Some of this looks redundant because we kind of did it last unit. However, if we're looking at the graph of vertical position versus time, you will get a quadratic equation where the A coefficient will wind up being negative 5 because it's a half of the acceleration in the y direction, right? Your B coefficient will be the initial vertical velocity, and the C coefficient will be equal to the initial position in the vertical direction. Notice on this slide, I substituted our position. Instead of using X, I used Y in order to highlight that we're thinking about the vertical position up and down as opposed to sideways. If you apply this same logic to horizontal position, right, we can still start with our position formula, but in this instance, the acceleration in the x direction is 0 because there are no forces pushing on the object sideways. So what happens is we start with our quadratic, but then this just cancels out. This is 0, and then we wind up getting an equation of a line where the velocity in the x direction, right, is our slope, and the initial starting location in the horizontal direction, right, would be our y-intercept. Click on this Desmos graph, put in an acceleration of 0, and you'll see that you get a line as opposed to a parabola. Okay. Make sure you do the interactive practice in these notes. Then you can move on to your Google Form practice and then eventually your week 4 project.